Hi everybody and welcome to the CERIAS Security Seminar at Purdue University. It is my great pleasure today to introduce one of my colleagues, Sarab Bakchi. He's an associate professor in the Electrical and Computer Engineering Department and also an assistant director for CERIAS. Sarab is going to talk today about protecting today's enterprise systems against zero-day attacks. Sarab.
This really does feel like being on TV, which I am told I am. This is my first time being on TV, so we'll see how it goes. Please stop me whenever you have any questions. I certainly expect this to be an interactive talk. And I have more slides than I can cram in 3 hours, so I don't certainly anticipate going through all my slides. So please ask me questions, clarification questions, challenging questions. Everything's welcome. So I'm going to present work that I have been doing jointly with several faculty colleagues and a student, Gasper Modello Howard, Alan Chi, who's a faculty here at Purdue, Guy Lebanon collaborated with us for some of the early work. He's at Georgia Tech now, and two researchers from Northrop Grumman. And this work has been funded by Northrop Grumman and the National Science Foundation. So let me start off by giving you an idea of what today's enterprise systems look like. They are almost invariably distributed. It's not a single box, but you have multiple machines which are connected via high-speed network links. And they have many users, both external and internal. So there are some services which are outward-facing, like web services or authentication services, which people from the outside of that enterprise should be able to connect to. And then there are some users who are internal. The environment for these are very dynamic in the sense that there is new software that gets put in, software that gets upgraded, and the software is oftentimes third-party software. So this is software that you don't have access to the source code for, and that you may not understand all the innards very well either. New users get added and new machines get added. So the attack surface for these systems, through which these systems can be penetrated, is quite large, changing, and growing. So this means that all of the dynamic factors that I just listed result in the fact that the attack surface keeps changing. So all the different ways in which an adversary can begin the compromise of the system. That's what's meant by an attack surface. And the attack may originate either from the outside or from the inside. So just like I mentioned to you, external users and internal users, obviously the attack can originate from the outside, but also an internal user may be the victim of an attack, and therefore the attack can originate from inside. Suppose you go in and you download some malicious payload from a website unknowingly, and so then the starting point of the attack becomes a machine which is inside the periphery of the enterprise. So this notion that you just guard the periphery of the enterprise and you're secure is no longer true. So here's a pictorial representation of our security scenario, and we are going to concentrate on something called a multi-stage attack. So the multi-stage attacks are those where the attack starts by compromising one particular service and then uses this as a stepping stone to get to other services. So for example, here you have a directory server, you have file server, you have a web server, various servers. Some of these are facing the outside, and some of these are protected inside in the enterprise. And the attack will start off, let's say, from the web server, then it will get to a connected server. So let's say in this case, you have the email server which is connected to the web server. So you will hop from the web server to the email server, and then from the email server you may hop on to the FTP server and slowly compromise more and more servers and get to the crown jewel which may be hidden well inside your enterprise. So this is what's meant by a multi-stage attack, and typically the way enterprises get compromised are through multi-stage attacks. And to protect against the multi-stage attack, you also have to place observation points in various parts of your enterprise system. So in this example, you have a sensor which is deployed on the web server, you have a sensor which is deployed on the FTP server, and so on. So rather than having just a single observation point in your enterprise, you have multiple observation points in your enterprise which are distributed all through the enterprise. So the first problem in securing enterprise systems is, where should I put these intrusion detection sensors? where do I place these IDSs? And once I place these IDSs, how can I configure these IDSs in the best possible manner? Because typically your intrusion detection sensors have a huge variety of configuration parameters. For example, do I want to match the rules corresponding to HTTPS or only HTTP? Do I want to match the payload, or do I just want to look at the headers of the packets? Do I want to look at packets which are originating from inside the enterprise or only ones which are coming from the outside? So there is a great variety of configuration parameters for these IDSs, and you also have to know how to configure these IDSs just right. And the way it works today is picking the right sensors, placing them and configuring them is really an art rather than a science, relying on dedicated security administrators who know the system really, really well, and even more importantly, who know how the system is evolving. We discussed a little while back all the different ways in which the system may evolve, and so they are knowing, these security administrators also have to know how exactly the evolution is happening. And a key insight is more detectors is not always the better, because there is the administrative cost of keeping these detectors updated. So I will use the term detectors and sensors interchangeably. So there is the administrative management cost of keeping these detectors continuously updated. There is the performance cost, that these sensors often will run on the same nodes as your application. So if you are going to dedicate a lot of the computational resources to running these sensors, that means that your applications are going to get slowed down. And then there is the economic cost of acquiring new machines, new sensors for protecting your system. So more is not always the better. So when you look at the way people typically in the enterprise handle these multi-stage attacks, it's a very ad hoc process. You take a look at the sensor alert streams coming out from each sensor, and you manually piece these together to say, okay, this is what must be happening. What I really want to know in protecting the enterprise is my crown jewel, which is hidden deep inside my enterprise, secure or not? And so what I conceptually want to do is to put together the alert streams coming from the different sensors and automatically, hopefully, figure out if what's happening to my crown jewel. And right now, this is very much a manual process, and the sensors today are not capable of keeping up with all the changes that I mentioned earlier. So maybe a new machine gets added to your system, a new user gets added to your system, your software gets upgraded. As a result, a new vulnerability opens up. So how can I automatically update my IDS configuration to match this is an unsolved problem. And that's exactly the problem that we set out to solve. Any questions or comments at this point? Okay, so the high-level solution approach is placing detection sensors at different points in my enterprise, and then providing the brains of the entire system, which is in a reasoning engine, which is going to take these alert streams from the different sensors, do its magic by putting together the different pieces of a jigsaw puzzle, and be able to tell you, one, which services in my system are compromised, two, how is the multi-stage attack spreading, and three, by putting these two pieces together, you can say, what is the likelihood that some crown jewel service of mine is going to be compromised? So these are the three things that I want my reasoning engine to be able to tell me. So in the first part of the talk, I'm going to tell you how we can do this distributed intrusion detection in a static environment, where I know what are the machines, what are the connectivities between the machines. I know that there are no new vulnerabilities that are going to be exposed in the system. The second part of the talk, I'm going to talk about when you have dynamism. And in the third part, I'm going to talk about how do you upgrade these intrusion detection sensors, the signatures, automatically to hopefully handle some attacks which you haven't seen in the past. So these are what are called the zero-day attacks. So I want to automatically generate the signatures. So the overall framework would be that we have an attack graph which is used to represent the way the attack can spread through the system. We're going to take that attack graph and convert that into a Bayesian network, which is going to be used for our inferencing. Now, with the Bayesian network and a set of available detectors, we're going to do the inferencing. We're going to do the evaluation of how good our inferencing is, and then we're going to have a feedback loop which says if my inferencing doesn't give me results that I'm very confident about, then I'll go back to the drawing board. I'll pick maybe different sensors, or I'll configure the sensors differently. So that's the overall framework. How many of you have heard of Bayesian networks before? So the Bayesian networks are a way of reasoning when you have uncertain information. If you had exact deterministic information, you could use something like a rule-based system, which says, if you see this, then this is what it means. If you see an alert with ID 1234, that means this particular service of yours was compromised. So this is very deterministic. What a Bayesian network lets you do is, in the presence of uncertain information, possibly noisy information, it'll give you a probabilistic estimate of what's happening. So you feed it some evidence, and it'll tell you what's happening in a probabilistic way. So digging a little bit deeper into the overall framework, we would use attack graphs as the input for our system. So attack graphs are a graphical representation of the different steps in which an adversary can get through into your system. And where the nodes represent individual steps of the attack, remember we talked about the stepping stone kinds of attacks. So the nodes represent the individual steps of the attack, and the edges represent the dependencies. So if you have a node A connected to a node B, it means once I achieve node A, I can use this privilege to now go ahead and achieve node B. So they're a fairly commonly used representation for multi-stage attacks. From the attack graphs, we're going to convert them into Bayesian networks for the purposes of doing inferencing. And using domain knowledge, or knowledge that we are going to be able to automatically extract from the system, we can provide annotations on these edges to indicate how difficult it is to go from a particular node to another node. So remember we talked about this A and B and an edge between A and B. So you want to annotate this edge between A and B to represent in a loose sense what is the difficulty of going from node A to node B. So once you achieve attack step A, it's not automatic that you're going to achieve attack step B. So we have some heuristics in order to calculate these values which will be used for the edges. So here's a very simple example of a fragment of a Bayesian network. So there are two notions in a Bayesian network in terms of the nodes. Some of the nodes are called the observed nodes or evidence nodes. So these are things that you will see in your system. For example, you will see an alert from an intrusion detection system. You will see an alert with a particular ID from an IDS. So that's your observed node. And the unobserved node is something that you want to infer, but you don't have direct proof or direct evidence as to what's going on. So for example, you want to know whether your web server is compromised or not. The way you get to know it is through the alerts of the IDSs, but you don't have a ground truth about is this web server compromised or not. So those represent what are called the unobserved nodes. So you have edges between the unobserved nodes like this, and you also have edges between an observed node and between an unobserved node and an observed node. So the annotation of an edge between two unobserved nodes quantifies the difficulty of going from attack step 1 to attack step 2. And the annotation on the edge between an attack step node and a detector node, an unobserved node and an observed node, is how good is this detector if this particular node is achieved. Okay? So this one is the true positive. This says that if this attack step A2 is achieved, with what probability will this detector D1 flag? So the ideal detector will have a value of 1 in here and a 1 in here. This says that if that attack step is not achieved, then what is the likelihood that this detector will not flag? So the ideal is 1 here, 0 here, 0 here, and 1 here. But detectors are non-ideal, and therefore those values will not be 0 and 1. So that's just a simple baseline about a Bayesian network. And what a Bayesian network inferencing does is you feed it the evidence. You tell it which detector nodes flag, and based on that, you can ask it the question, what is the likelihood that a particular attack step has been achieved or not? So based on observed nodes, it will give you a probabilistic inferencing about the unobserved nodes. So that's what a Bayesian network is all about. And it does this very, very efficiently under certain assumptions. Assumptions like this graph cannot have cycles in it. So as long as those assumptions are true, it does a good job of doing the inferencing in a very efficient manner. Okay, so this is a sample network and the Bayesian network corresponding to it. So the sample network is right here. So you have a firewall. This is the big bad internet which is outside of the firewall, and this is inside the periphery. So you take that and you convert that into a Bayesian network through a tool that we've developed. So what this tells you is all the different ways in which the attack can spread through the system, and these red nodes correspond to the one particular placement of the intrusion detection sensors that you have. So you may place a firewall in here, a network-based IDS in here, a buffer overflow detector in here, and a database-based IDS in here. Yeah. So those were the first two steps. Now, once you've done these first two steps, remember what we're trying to do is to pick detectors in order to best detect some crown jewel nodes that I have in my system. So we formulate this formally as a 0-1 knapsack problem. So if you remember your basic undergraduate algorithms course, a 0-1 knapsack problem is I have a knapsack and I want to put some weights in it. I want to put some things in it, some items in it. Each item has a weight and a benefit. So if I put more than the specified weight into my knapsack, then it'll tear. So I want to optimize that. I don't want to put more than what that knapsack is capable of carrying. And each item that I put into the knapsack has a benefit value. So I want to maximize the benefit of all the items in the knapsack subject to this weight constraint. I don't want it to exceed this weight. So it turns out that that's a good way of formulating our problem here. Each intrusion detection sensor gives you some benefit, but it also has a cost to it. So we quantify the benefit from an intrusion detection system, each sensor, and we also quantify the cost from it. So what could be the costs of putting an IDS in place, do you think? Anyone? Running out of resources. So remember we mentioned that they run on the same machine on which your entire application is running. So they're going to take away some cycles, either compute cycles or memory from your application. And IDSs tend to be very, very resource intensive. So what are some other costs that you could have from your IDS? So another cost is your IDS is going to have some false alarms. So whenever you have a false alarm, you have to have somebody chase this up and find out really what's going on. So there is a cost because of that. So there is some magic that goes in whereby we quantify these costs, and the benefits are obvious. If the sensor really works as it's supposed to work, then it's going to be able to tell you quite accurately whether those crown jewel nodes that you're really interested in, what the status of those are. Is it compromised or is it good? So that's the benefit. So the original 0-1 knapsack problem, and it's called 0-1 because you can either keep an item or not keep an item. You cannot get fraction of an item. That's why it's a 0-1 knapsack. So it's an NP-hard problem where the computational cost for this grows exponentially with the number of items that you have. So since the number of intrusion detection sensors that you have to choose from and their placements, that's a fairly large search space. So if you wanted to solve this exactly, it's going to take you very long. And remember, here we're trying to solve this problem on the fly. As the attack is going through your system, you want to be able to say, oh, let me move a sensor from here to this point, and that will give me a better idea of what's going on in my system. So speed is of essence in here. So we come upon something called FPTAS algorithm. So this class of algorithms has this nice property that you don't get the optimum solution, but the computational cost for those is a function of how close you are to the optimum. So if your epsilon was, what would epsilon have to be for this to give you the optimum solution? So the solution that you're getting from this is 1 minus epsilon times optimum. For what value of epsilon would you get the optimum solution? Huh? 0. So for epsilon of 0 you get the optimum solution. But you see what happens to the running time when your epsilon becomes smaller and smaller. Right? So here you can trade off how close you get to the optimum with the time that it takes for you to run this algorithm. So that's a nice property of these FPTAS algorithms. Fully polynomial time approximation schemes. So we do this and we run the FPTAS algorithm, and you would compare this to the greedy scheme. So what do you think would be the greedy scheme, the simple algorithm? How do you come up with a greedy scheme for this? So the greedy scheme is very simple. It says, let me pick the sensor which gives me the greatest ratio of benefit is to weight. Let me pick that. Okay, now I see how much weight is still left. Now I go in and pick the next sensor, and I keep going till till I've reached the weight limit of my knapsack. So that's the greedy algorithm. Right now, the greedy algorithm doesn't work the best in these scenarios because these sensors are not completely independent. Which means, let's say I place a sensor right at the ingress point, which is able to do an examination of all the traffic which is coming into my system. So this may render a sensor placed inside useless, because this guy is already seeing all the traffic that's coming in, and it's matching all the rules that this sensor which is deep inside would be doing. So this is an example where these sensors are not completely independent. And if they're not completely independent, a greedy typically doesn't give you the best solution. Right. So to evaluate this, we take a representative e-commerce system. We create the Bayesian network. We also do this with a voice over IP system. And this is the crown jewel. So if this service is compromised or if this attack goal is achieved, then all is lost in our system. And you can run this for various values of this error parameter epsilon. So expectedly, as epsilon gets closer to 0, the quality of your solution improves, but the running time also increases. Right? So we find that the values of epsilon equal or larger than 0.01 allows the FPTS to run faster than the greedy approach for comparable quality. Okay. So if you allow about 1% away from the optimum, then you can run faster than the greedy. That's what this result is telling us. So this told us what we will do if nothing changes in your environment, if everything is static. Now let's see how we would handle the case when things are more dynamic, when the environment is changing. So in what different ways can your environment change? So there could be connectivity changes, meaning that now your machines are connected in different ways. Maybe you've erected a firewall rule which now made two machines which were originally disconnected, now they're connected. And if you increase the connectivity, that means an attacker can hop from this machine to this machine because now they're connected. Another way is new attacks are discovered, so your attack graph will have to change. And the other is there may be new users added to your system. So we have different algorithms which will be able to update those attack graph and the Bayesian network corresponding to these different changes. And I'm only going to talk about one of those four algorithms. So algorithm 1, whenever there are connectivity changes, I have to update the Bayesian network corresponding to it. So to look at what connectivity changes there are, we look at firewall rules. So which do you think is the most common example of firewall in Linux environments? Has any of you used firewalls in Linux? IP tables. So IP tables rules, you can use those IP tables rules for deciphering if there are connectivity changes, and that's what we do. So each node has a conditional probability table in the Bayesian network, and we will update this conditional probability table of the Bayesian network based on rule changes in your IP tables rules. So your IP table rules will have a format like this. This is the source IP address, destination IP address, the port number of the destination, what kind of action you want. Do you want these packets to be dropped or forwarded or what have you? And then an enumerated list called rule type. So we'll take the input of all the IP tables rules and we'll output a list of nodes and edges that should be added to or deleted from the Bayesian network. So in the Bayesian network, remember, you had nodes and edges. So based on changes to the IP tables rules, you will either add or delete nodes and edges from the Bayesian network. So this algorithm, if you look at it in more detail, you could determine which nodes and edges are to be added. You could determine which nodes and edges are to be deleted. And then remember, for Bayesian networks, we said that efficient inferencing can only happen if there are no cycles. So it may so happen that because of all these changes, you may generate a cycle. So then you have to delete some edges so as to remove the cycles. And then you have to convert these destination IP address and port nodes into Bayesian network nodes. So Bayesian network nodes represent attack steps. So there is a conversion from this destination IP address and port to address, port, and vulnerability. Okay, so for the experimental setup, we take a real-world distributed system that we have as part of a National Science Foundation center here at Purdue called NISCOM. We generate the corresponding vulnerabilities by using a widely used vulnerability scanner called OpenVAS. And then this vulnerability scanner will generate a huge number of vulnerabilities. It also classifies those as high, medium, and low. So we remove all the medium and low vulnerabilities and we focus only on the high vulnerabilities, high-risk vulnerabilities in there. So that leaves us with a Bayesian network with 90 nodes and 582 edges. And there are 18 possible detectors that we can place in this system. And remember, we said that more is not always the better. So it's not as if we would really want to go ahead and pick all 18 detectors. So we put a constraint in our system to say that only pick no more than 6. And then you would compare the result of this distributed intrusion detection system to something where you're chosen based on some heuristic. So in an ad hoc manner. This is chosen in an ad hoc manner. So this is the overall network structure. So I certainly don't expect you to understand the details. The high level is that there is an internal network where the developers' machines are and the consultants' machines are. There is a production environment. This is where the production workload runs. And then there is a development environment. And there are connections between the internal network, production environment, and the development environment. So typically, once you develop something, you field test it in here before you push it out to the production environment. And so this results in the Bayesian network, which we automatically generate. And then we try out various multi-stage attack scenarios. So these multi-stage attack scenarios are based on real vulnerabilities that are found in each of these softwares. So CVE is a most popular vulnerability database. And so this has the CVE number, which means it's a unique characterization of the vulnerability. So, for example, this is an attack which originates from external, from the internet, and these two are attacks which originate from inside the network, from developer 1's machine and developer 2's machine. So here's just a snapshot of the result, one snapshot. So you compare the performance of our dynamic reconfiguration system with a static set of detectors. So with a static set of detectors, somebody has gone in and put on his thinking cap and placed the sensor. So remember, we are only allowed to place 6 sensors in this environment. With the dynamic one, what happens is, once you receive alerts from the first 3 attack steps, the system can go ahead and reconfigure the sensors. So it can say, oh, I have a sensor which is placed on this service. That sensor doesn't seem to be very useful for this attack scenario. Let me take it from there and move it to a different service. And what this result is showing is on the y-axis you have the true positive rate, and on the x-axis you have the false positive rate. So for an ideal situation, where do you think the point should be? So if you think of this, so this is 0, 0, this is 0, 1, and this is 1, 0. So for an ideal situation, where would you want your point to be? Anyone? 1, 0. So 1, 0 would be here. 0, 1. So 0, 1 would be here. That would mean that your true positive rate is 1, which means you're catching all the attacks, and your false positive rate is 0, which means you're not flagging anything which is a legitimate action. So that's your ideal point. So the closer you can get to that ideal point, the better you are. And of course, the reason I'm showing you this result is because our system gets closer to the ideal point. If these were flipped, I would never show you that result. So the takeaway from this is, if you can react to the first few attack steps and reconfigure your system, then you're better off than a static, heuristically chosen placement of sensors. So now I'll go into the third part of the talk, and I'll gloss over the details here and only give you the basic intuition behind it, and leave some time for a question and discussion. So a big issue with all of the intrusion detection systems are that they are based on signatures, which say if you see this, then that's malicious. Now, when you have signatures like that, you have to manually update these signatures as new attacks get exposed. That's a Herculean task. So this means that you have to have lots of people who are dedicated to constantly looking at these new attacks as they're coming in and manually figure out how they can modify an existing signature. What you don't want to do is for every new attack sample to create a new signature, because at runtime you have to match these signatures. So if you have a million signatures, it will take you forever to match these million signatures. What you rather want is to create a regular expression and add to this regular expression incrementally as new attack samples come in. So those people who have to do this for their day job are they're usually not the happiest people around, because they're looking at these very complicated attack samples and they're looking at these humongous regular expressions. So you have to tell me one attack sample which will match this regular expression. So there are people who have to do this as their day job. And as a new attack sample comes in, they have to figure out, oh, I should probably drop this question mark in here so as to be able to include this new attack sample. So we talked to the people who do this for two widely used intrusion detection systems, and we've actually spoken with the people who do this for their day job, and they agreed that this is an extremely tedious manual process. So what we've really done is provided an automatic approach to generate and update signatures for these misuse-based, network-based intrusion detection systems, and we've created a framework to generalize existing signatures. So you give me a set of 6 signatures that you have. As new attack samples come in, can I broaden this out so as to be able to include these attack samples? So the very high-level overview of doing this is these 4 steps. And we call this P-SIGENE, or SIGENE, with the P being silent, as in psychology. So it stands for signature generation, and you have to sort of look at it differently to make sure that it works out. But that's the best name that we could come up with, which is pronounceable. So what we first do is we do web crawling to find out lots of attack samples. So we generate a data set. Then from this data set, we do what's called a feature extraction. So these are the different features in my data set. So specifically, we've done this for SQL injection. So what are features? Features could be the number of times you have the keyword select. The feature could be the number of times a select is followed by a table name of T1. So those are features. So you extract the features from it. Then you do clustering of these features. So clustering, as the name implies, is you will have samples. So let's say these 100 samples fall in cluster 1, which means that they're similar. These next 500 samples fall in cluster 2. So we have to have an automatic way of doing this clustering. So the idea for the clustering is that you don't want to treat every single attack sample by itself, because then your analysis is just going to blow up. You want to treat them as groups which are similar. So from this training set, this is called the training set, because here we know that these are all malicious attack samples. We will create these clusters, and now through a logistic regression algorithm, we'll generate a signature, one for each cluster. So we'll have one signature for each cluster. So now, at runtime, what will happen is a new SQL query comes in. We will pass it through all these signatures. If it doesn't match with any of the signatures, we'll say, oh, this is good. So notice that what we've done here is automatically created new signatures. Now there's a lot of devil which lurks in these details. Right? So very difficult parts of this is, how do you do this web crawling and clean out the samples? Another difficult question is, how do you extract these features? What do you call as the features? Another challenging question is, when you do the clustering, what kind of clustering algorithm do you use, and how do you define the parameters for the clustering algorithm? Like, what is the distance metric? And the fourth one is, when you're creating the signatures out of these clusters, we decided to use logistic regression, but within the logistic regression, again, there are parameters which says, am I going to use every single feature within that cluster, or there are some features which are very distinctive of that cluster. So we want to zoom in on those features which are very distinctive in that cluster. So these are all the difficult technical challenges that we've solved partly. I think you never solve a problem completely, because then you'll be out of work. So you only solve it good enough that you're making progress, but it's not completely solved. So we focus on the SQL injection attack for obvious reasons. You hear of SQL injection attacks all over the news. And in our evaluation, what we do is we look at the accuracy and precision of the signatures that we generate. So accuracy corresponds to, for malicious attack samples, how often are you catching them? Precision corresponds to, for non-malicious samples, how often are you, or how often do you not flag? So high accuracy is good, high precision is good. Then a big part of this work is also incremental learning. So you already have a system in place. You see some new attack samples. Can you incrementally learn and update these signatures? So we evaluate that. And then performance is always important, because the matching of the traffic happens at runtime. So it's not as if traffic comes in. You can put it off to the side and take your own sweet time to match it, and then let the traffic pass. This has to be fast because it's being done at runtime. And we incorporate our signatures into a very popular IDS called Bro, and then run our experiments. So this is what these signatures today look like for these four very popular SQL injection detection systems. Bro and Snort are network-based intrusion detection systems, but they also have rules specifically for SQL injection detection. So 6 rules in here with those humongous long rules, 79 in here, and emerging threats and mod security are very, very focused on SQL detection. So lots of rules, and some of the rules can be very, very long. So these are in terms of the number of tokens. So you need a training data set, you need a data set, a test data set. Within the test data set, you need attack samples, and you need non-malicious or benign traffic. So this lays out how we get the training data set with 30,000 SQL injection samples, which we get by web crawling, going to dark parts of the internet, which you are usually not recommended to go to, where people post SQL injection attack samples. So you have to be very, very careful while doing this experiment. Otherwise, you can easily have these attacks run in the wild, not completely hose your computer, but also the computers of people around you. And then these are for the benign traffic, And this is the data set for testing with the malicious attack samples. Okay, so this is actually quite important that you get a representative enough sample for your training data set. So this is the true positive, false positive. This is SciGene, which is our technique. And 9 and 7 refer to the number of clusters that we have. So more number of clusters, fewer number of clusters. So we find that the true positive rate of even the best system is less than 100%. Okay? And mod security is the one which is very focused towards SQL injection attacks. So we are in that 80 to 85% range. The false positive rate of Bro is 0. So they have no false positives with our training, with our test data set. Whereas all the others, including ours, have some false positives. So while this 0.037% number may look pretty small, it translates to 523 false positives with this data set. So with 7,258, no, not this one. With 1.4 million HTTP GET requests, 523 of them will flag an alarm, and these would turn out to be red herrings. So it's important to keep in mind not just the percentage, but absolute numbers too. So 0 false positive is really good in this respect. Mod security turns out has a very robust signature set, something that's been developed over the years with a lot of careful attention to details. And then further, you can go in and look at the quality of the individual signatures. So with 9 signatures, or with 11 signatures, no, 9 in this case, you can go in and see the true positive and the false positive rate of each of the signatures. And then you can decide which ones to keep, which ones to throw out. And the takeaway here is that there is quite a wide variability in the quality and the coverage of the signatures that we generate. The performance evaluation, certainly it's quite expensive as of now, but that's because we haven't optimized it completely. It's 11x the cost for ModSec and 19x the cost for Bro, the slowdown. And there is a particular function in Bro which we call many times called count all, which turns out to be quite expensive because it needs to go back and forth over the SQL query. But the good news is that the worst case processing time, even on a crummy laptop, is less than 2 seconds. And this is something that's very easily parallelized. So if you have 9 signatures, a packet comes in, you can make this packet run in parallel against the 9 signatures. So this is what's called an embarrassingly parallel kind of an application. So to conclude, what we've done in this piece of work is we've designed a distributed intrusion detection system which would be very tailored to detecting these multi-stage attacks, which are the ones which are targeted against enterprise systems. And we've developed this system called SciGene, which can automatically generate and update the intrusion detection signatures. And we've tested this only for SQL injection attacks, which means there's a lot more work that still needs to be done. And we have this fairly heavy-duty machine learning algorithms for clustering and regression to come up with the signatures from these attack samples. So there's a lot of future work, which means interested students here, there's a master's thesis, PhD thesis to be done on all this work. How do you, instead of looking at the intrusion alerts purely as 0 1s, can you look at the confidence values from these alerts and use that in your inferencing? Can you incrementally deploy these IDS sensors? So let's say with an enterprise, you have a particular setup right now. If you go in, provide a solution which says, oh, throw out this setup completely and put new sensors, new configurations, nobody's going to adopt your solution. So you want to do this in an incremental manner. You want to say, okay, keep most of what you have and let me just twiddle a few knobs in here to give you a better performance. So that's important practical consideration that needs to be taken into account. And again, can I incrementally update the signatures as more attack samples are discovered? The way I presented the solution, it's a batch mode solution. You feed all the attack samples into our system, it spits out signatures. But in reality, what will happen is you have some signatures. After each day, you will get some more attack samples. Can you incrementally update these signatures? There's a lot of related work. So if when you're really bored, you can start reading these papers going back to 1999. There's papers in pretty much all the aspects that we've covered in here. Oh, there's even 1991. So if you're interested in the project, want to try out our system, please visit the website of our group, the Dependable Computing Systems Lab. And as I mentioned, there are a few master's and PhD theses lurking in their future work. So contact me if you're interested. I'll take any questions.
Could you go back to the slide that had the false positive rates compared? Thank you. When you have 9 clusters, it seems almost like that should allow you more expressiveness in the features that you're looking for, but your false positive rate went up. Could you comment as to what you think happened there?
So why the false positive rate for 9 clusters is higher than with 7 clusters? So the way we come up with 7 clusters is we discard some of the samples. So which means we have fewer signatures in here corresponding to here, which means we are covering a smaller part of the training data set in here. So fewer signatures means you'll not be able to catch as many of the attacks in practice, but it also means that your false positives will be smaller.
Oh, so it's not that you imposed a restriction on the number of clusters that could be formed, it's that you excluded
Discard
some. Okay,
right?
thank you.
So you'll find out the smallest clusters and you'll say, okay, this is not very representative, let me throw those out.
Okay.
Any other question? Okay. How do I end it?